Hey everyone, welcome to this explainer. Today, we're actually going to trace the exact path that connects the physical world to the digital one. We're going to take a micro to macro journey. So we'll start with the invisible flow of electrons, and then we'll zoom all the way out to simulating massive digital IoT networks. Let's dive right in.
All right, so here's our blueprint for today. Section 1 is electronics and circuit basics. Section 2, understanding electronic components. Section 3 covers the hardware prototyping journey. Section 4 is all about microcontrollers, sensors, and actuators. And finally, Section 5, simulating IoT systems.
Starting off with Section 1, electronics and circuit basics.
You know, the fundamental challenge of the Internet of Things really just boils down to one thing: controlling the physical flow of electricity. We are starting literally at the atomic level here, because long before we're dealing with code or the cloud, we're fundamentally dealing with physics, specifically directing the flow of electrons through conductive materials.
To actually control those electrons, we have to rely on Ohm's law. Basically, it states that voltage is directly proportional to current multiplied by resistance. For IoT design, this relationship, it's absolutely crucial. It's your golden rule. When you're out there building low-power sensors for the field, balancing these variables is exactly what determines whether your edge device is going to run for a single day or for a whole decade.
And all these variables come together beautifully in a closed circuit. In a standard setup, you'll see a power source, like a 6-volt battery, providing the current, while a component like a 2.2 kilo-ohm resistor actively restricts the flow. That resistor is there to protect the LED from drawing way too much current and just burning out. This simple, perfectly balanced loop is literally the foundational building block for pretty much every IoT device out there.
Moving right along to Section 2, understanding electronic components.
So once we actually have that basic circuit down, we start introducing specialized components to really control that current. We generally group these by behavior. Active circuits use components, like transistors, that actually rely on an external power source to deliberately direct the current flow. It's kind of like a traffic cop. On the flip side, passive circuits use components like resistors or capacitors. These guys don't control the flow, they simply react to the energy passing through them based on their own physical makeup. We also have to make sure we match the power source to the device itself. Now, massive infrastructure, right, that runs on alternating current, which is where the electron flow periodically reverses direction. But the vast majority of our small edge IoT prototypes, they operate on direct current. They're drawing steady, one-way power straight from things like batteries or solar cells.
Now, the really crucial piece here is how these components communicate with each other. Analog circuits use continuous signals that flow in smooth waves, basically representing a whole spectrum of real-world values. Digital circuits, however, use discrete binary blocks, your ones and zeros. And because the real world is inherently analog, our IoT devices are constantly having to translate those smooth, continuous curves into discrete digital data. It's a constant translation game.
All right, Section 3, the hardware prototyping journey.
Okay, to group all these individual pieces together into a working device, we have to enter the prototype phase. And this usually follows 4 distinct steps. First, you're developing the hardware and software simultaneously, often just starting out on a messy solderless breadboard. Next up, you map out a custom circuit board layout. Then, you build out your physical iterations. And finally, you put that device through some rigorous product testing to see if it holds up.
And hey, if your design survives the prototyping phase, it graduates to the production phase. This is where we get manufactured printed circuit boards, or PCBs. So instead of a jumble of loose wires on a temporary breadboard, the whole circuit is permanently etched right into these boards. Now it's finally ready for mass deployment and, actual real-world conditions.
Which brings us to Section 4, microcontrollers, sensors, and actuators.
Okay, so we've basically built the body of our device. But now we need a brain. And a really great way to visualize this is through prototyping bundles, like the SparkFun Inventors Kit. Right at the center of the action is an Arduino microcontroller. Think of it as a tiny computer sitting on a single integrated circuit. It acts as the completely programmable command center. Once it's wired up to a breadboard, it's just sitting there, ready to receive your commands.
But how do we give it those commands? Well, we use an integrated development environment, or an IDE. By writing programs, which we call sketches, and utilizing basic structures like setup and loop functions, we completely bridge the gap between software and hardware. We're taking this C-based logic, compiling it, and literally flashing it directly onto the microcontroller's memory to dictate exactly how it behaves.
And once that code is up and running, the microcontroller starts interacting with its environment using two main categories of components. First, you have sensors. These act as your inputs. They detect events like shifts in light or a physical flex, and then they send electrical signals straight back to the brain. Then you have actuators. These are the physical outputs. They're your motors or relays that receive an electrical command from the microcontroller and convert it directly into mechanical movement. So the cycle is really just sense, process, actuate.
Finally, Section 5, Simulating IoT Systems.
So, what happens when you want to scale all this up? Like moving from a single breadboard to a smart system for an entire city? Well, professionals use software like Cisco Packet Tracer as a massive digital sandbox. It lets you pull virtual single-board computers, sensors, and actuators right onto your screen. You can connect them all up to model the data flow across an entire end-to-end network. It's absolutely incredible because it allows you to stress test your logic and architecture before you ever deploy a single piece of physical hardware.
So, bringing it all together, we've just traced a complete path. We mapped out the flow of electrons using circuit schematics, we gave those circuits a programmable brain using microcontrollers, we enabled physical interaction with the real world through sensors and actuators, and finally, we scaled those individual edge devices into massive digital networks through simulation. It's the whole shebang.
Which leaves us with just one final question. Now that you really understand the fundamental building blocks that connect the physical world to the digital, what kind of IoT device are you going to build next? The hardware is accessible, the concepts are right there in your hands. It's time to open up an IDE and start prototyping. Catch you next time.